Hello students, so welcome to today's class. Today we will be doing Ionic equilibrium question part 4. Disclaimer, the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. So, in this session, we will be practicing questions from 28 to 34. Question says that at 25 degrees Celsius, the solubility of MgOH whole twice is 1 into 10 to the power minus 11. At which pH will Mg2 plus ions start precipitating in the form of MgOH whole twice from a solution of 0.001 molar Mg2 plus ions? Options are A 9, B 10, C 11, and D 8. Your time to solve this question starts now. Your time is up. So in this question, two data are given. First is the solubility product. Okay, solubility product, that is Ksp is given as 1 into 10 to the power minus 11. Second thing, your concentration of Mg2 plus ion is also fixed. It is 0.001 molar. Clear? Now you have to find that at what pH will this criteria will be satisfied. Okay. Correct answer is B, which is 10. So pH should be 10. We know that your magnesium hydroxide will dissociate into magnesium 2 plus and 2 moles of hydroxide ion. So how we will calculate Ksp? So Ksp will be simply concentration of the magnesium 2 plus ion multiplied by the concentration of OH minus, that is hydroxide ion, raised to the power 2. Okay. Now, how can we calculate OH minus concentration or hydroxide concentration? So we will simply take the root of Ksp by magnesium 2 plus ion concentration, and that should be coming out to be 10 to the power minus 4 molar. Okay, if you put the values, you will get this. So POH will be how much? POH will be 4. Very simple. Take the log of this 10 to the power minus 4 and put a negative sign against it, and you will get the POH as 4. Then 14 minus 10, which is your pH, comes out to be 10. Okay. Next question. The precipitate of CaF2 Ksp is given as 1.7 into 10 to the power minus 10 is obtained when equal volumes of the following are mixed. Option A, 10 to the power minus 4 molar Ca2 plus and 10 to the power minus 4 molar F minus. Option B, 10 to the power minus 2 molar Ca2 plus and 10 to the power minus 3 molar Fe minus, F minus. C, both option A and B. D, none of this. Your time to solve this question starts now. The time is up. In this question, we are given the Ksp value of calcium fluoride. And now what we are doing is we are taking equal volume of both ions, that is fluoride ion and the calcium ion, calcium 2 plus ion. And you have to say that what is the volume, what is the molarity that you will take so that the Ksp value can be satisfied. Correct answer is B. That is, we can take 10 to the power minus 2 molar Ca2 plus and 10 to the power minus 3 molar F minus. Now, if we consider the dissociation of the calcium fluoride, it will dissociate as calcium 2 plus and 2 moles of fluoride ions. So when will be the precipitation occurring? It will occur when the ionic product is greater than Ksp. So this is the condition. Okay, if your ionic product is greater than Ksp, then you will be able to notice precipitation. So this thing is happening in option B, right? This thing is happening in option number B. So if you take 10 to the power minus 2 into 10 to the power minus 3 of this, and you will take the square because F has a coefficient of 2. So we'll take the square of the F minus concentration. So this thing is coming out to be, so 3 to the 6 plus 2, 8. So that is 10 to the power minus 8, which is greater than the 10 to the power minus 10 value. So option B is saying it very clear that your ionic product is having greater value than the solubility product. Clear? Okay. So this thing is given. So correct option is B accordingly. Next question. The Ksp for CrOH whole thrice is 1.6 into 10 to the power minus 30. The molar solubility of this compound in water is, options are A, root under 1.6 into 10 to the power minus 30, B, 1.6 into 10 to the power minus 30 raised to the power 1 by 4. Option number C, 1.6 into 10 to the power minus 30 divided by 27 raised, and this thing is whole raised to the power 1 by 4. Option number D, 1.6 into 10 to the power minus 30 by 27. Your time to solve this question starts now. Your time is up. So we are given the Ksp value, okay, and you have to find the solubility for the given salt, which is chromium hydroxide. Correct answer will be C, root under 1.6 into 10 to the power minus 30 by 27, where root is having a power of 1 by 4. Okay, this is not a square root, this is a quadruple root. Okay. So if you consider that S is the solubility of the given salt, okay, then it will dissociate as Cr3 plus and 3OH minus. So how can we write the Ksp? Very simple. Concentration of this chromium 3 plus multiplied by concentration of this hydroxide ion, and that is having a power of 3 because the coefficient is also 3. So if S is the concentration, S is the solubility of this, right, then we will get S as the solubility of Cr3 plus, or the concentration of Cr3 plus I would say, and 3S as the concentration of the hydroxide. Now we have to take the cube of this, and if you put the value of Ksp here, so now using this simple equation we can calculate our S. So 3 cube is 27, and this will be as it is, and S into S cube will be S to the power 4. Now S will to the power 4 can be written as 1.6 into 10 to the power minus 30 by 27. Or we can calculate S, or the solubility as root under 1.6 into 10 to the power minus 30 by 27, where root is having 4 here. Okay. Next question. The solubility of AgBrO3 in an aqueous solution of NaBrO3 as compared to that in water is, options are A, the same, B, more, C, less, D, unpredictable due to new chemical reaction. Your time to solve this question starts now. The time is up. So we are being said that the solubility of AgBrO3 in an aqueous solution of NaBrO3 is how much? So it will be less than the general one, means the normal solubility will be less, means the normal solubility will be greater. Okay, and in this case you will get a less solubility in compared to the normal one. NaBrO3 dissociates as Na plus BrO3 minus. Okay, we know that, it is very clear from the given formula. Our AgBrO3 will dissociate into Ag plus and BrO3 minus. Now, due to the common ion effect of these ion present in both salts, the solubility of AgBrO3 in aqueous solution of NaBrO3 is suppressed, because now we have already the concentration of BrO3 minus coming from the sodium salt. Therefore, the amount of AgBrO3 that will be dissolved will become less automatically. Clear? Okay. Next question. The solubility of AgI and NaI solution is less than in pure water because options are A, AgI form complexes with NaI. Option number B, of common ion effect, C, solubility product of AgI is less, and D, the temperature of the solution decreases. So your time to solve this question starts now. Your time is up. In this question, we are being said that the solubility of AgI and in NaI solution is less than in pure water. Okay, so AgI is less soluble in the NaI solution in comparison to the pure water solution. So you have to say that what is the reason. So the reason is simple. It is because of the common ion effect. So when we dissolve AgI in the water, we get Ag plus and I minus. Okay. Similarly, if we dissolve NaI into water, we will get Na plus and I minus. Now there is a common ion present in both of them, which will result in the common ion effect. Right? So due to this common ion effect, the AgI solubility is suppressed. Next question. 0.1 mole of CH3NH2, whose Kb is 5 into 10 to the power minus 4, is mixed with 0.08 mole of HCl and diluted to 1 liter. What will be the H plus concentration in the solution? Options are A, 8 into 10 to the power minus 2 molar, B, 8 into 10 to the power minus 11 molar, C, 1.6 into 10 to the power minus 11 molar, and D, 8 into 10 to the power minus 5 molar. Your time to solve this question starts now. The time is up. In this question, we are given a weak base whose Kb value is 5 into 10 to the power minus 4, and we are taking 0.1 mole of that base. Now we are mixing that thing with 0.08 mole of HCl and diluting the whole solution to 1 liter. You have to say that what will be the H plus concentration in the given or in the for the resultant solution. Correct answer will be B, 8 into 10 to the power minus 11 molar. Now, since our base on reaction with HCl will give a salt of weak base and a strong acid, it is very obvious. HCl is strong and your methylamine is weak. So you will get a salt of weak base and a strong acid. So at time t is equals to 0, we will have this 0.1 mole of methylamine and 0.08 mole of HCl. Okay. Now after the reaction, if whole of the HCl is being reacted, then that will result in 0 mole of HCl. And if 0.08 mole of this HCl reacts with 0.1 mole of methylamine, then only 0.02 mole will be left for the methylamine, and the salt that will be formed will amount to 0.08 mole. So this is the final concentration of each species, where methylamine is 0.02 mole, HCl is 0, and your salt is 0.08 mole. So this thing will act as a buffer because of the presence of weak base and its salt. So this is the weak base and this is its salt. So this whole solution will act as a buffer, and the solution will have a volume of 1 liter. So what is the calculation that is used for the calculation of this pOH? It is pOH is equals to minus log Kb plus log by salt by base, log salt by base. So this is for the buffer. Now we have salt as this CH3NH3 plus Cl minus and base as your methylamine. Now putting the value of Kb, which is 5 into 10 to the power minus 4, it is given, and the concentration of salt, which is 0.08, divided by the concentration of methylamine, which is 0.02. If you put all the values, you will get your pOH as 3.90. Very simple. 0.08 by 0.2 will be log 4. Okay. Now this will be how much? So minus 4 log 10 to the power minus 4 will be 4 log 10, obvious, and this will be minus log 5. So 4 log 10 minus log 5 plus log 4. So upon calculation of this log 5, you will get it as 0.699. and 4 log 10 will be simply 4 because log 10 value is 1 and log 4 value is 0.0602. So our answer comes out to be 3.903. Therefore, the pH of the solution is 3.903. What will be the pH? This is the pOH. What will be pH? It will be 14 minus 3.903. So that will give you 10.0097 as your pH. And that is nothing but the negative logarithm of this H plus concentration. Now, how we'll calculate the H plus concentration? Simply take the anti-log, that will give you 8 into 10 to the power minus 11 molar. This is your answer. Next question. Which of the following will produce a buffer solution when mixed in equal volumes? Options are A, 0.1 mole per decimeter cube NH4OH and 0.1 mole per decimeter cube HCl. Option number B, 0.05 mole per decimeter cube NH4OH and 0.1 mole per decimeter cube HCl. Option number C, 0.1 mole per decimeter cube NH4OH and 0.05 mole per decimeter cube HCl. And option number D, 0.1 mole per decimeter cube CH4COONA and 0.1 mole per decimeter cube NaOH. Okay. Your time to solve this question starts now. The time is up for this question. So we have to say that out of the given buffer, which will out of the given solution, not the buffer, out of the given solution, which will form a buffer solution if they all are mixed in the equal volumes. Correct answer will be C, that is 0.1 mole per decimeter cube of NH4OH and 0.05 mole per decimeter cube of HCl. So when the concentration of NH4OH is higher than the strong acid, then what we will get? So since you know that the concentration, you can see it very, very clearly from here, that the concentration of this weak base is greater than the concentration of this strong acid. And since we are taking the equal moles of this, that means your whole of the HCl will be consumed and only your weak base will be left. So you have a weak base, okay, and the salt or the conjugate acid that is obtained during the reaction. So you have the two things. Now this thing is very good for the action of buffer. So this is your buffer. And what kind of buffer? Since we are having a base left at the end of the reaction, therefore it is a basic buffer. Clear? So if you take the reaction here, we can see it very clearly that initially we have 0.1 molar NH4OH, okay, and we have 0.05 molar HCl, right? Till now, no salt has been formed and water is taken as unity, or you can say it as infinity, right? So after the reaction, since your HCl is present in low concentration, so it will be used up. So 0.05 will be, if this amount is used up, then 0.1 m will be left. 0.05 m will be left for the ammonium hydroxide. And the same amount, because the stoichiometric coefficient is 1 throughout the reaction, so same amount of ammonium chloride will be formed on the product side. So this is your salt. So at the end of the reaction, you have a weak base and you have its salt. Now this solution will properly act as a buffer. So your answer comes out to be C, which is 0.1 mole per decimeter cube ammonium hydroxide and 0.05 mole per decimeter cube HCl. Thank you. This was all for today's session.